This video was produced by the UCD Math Support Centre in conjunction with the UCD Access Centre. Previously, we looked at one sample of size n taken from a population, and we calculated statistics such as the standard deviation and mean of this sample. However, what happens if we take more than one sample from the population? If we take all possible samples of size n from a population and we calculate a statistic for each sample, for example, if we calculate the mean for each sample, we can make a histogram of all our sample means and how frequently each sample mean occurs. From this, we can develop a probability distribution of the mean. This will be known as the sampling distribution of the mean. The mean of our sampling distribution will reflect the mean of the population. The standard deviation of our sampling distribution, referred to as sigma subscript x bar, is given by sigma over the square root of n. We will see this being used at a later stage to develop confidence intervals. When we are dealing with the sampling distribution, our z-score formula changes. Previously, our z-score formula was x minus mu over the standard deviation. Now, however, for the sampling distribution, we use z is equal to x bar minus mu all over the standard deviation of the sampling distribution, which is x bar minus mu all over sigma divided by the square root of n. Let's try a question using the new sampling distribution z-score formula. The question states, a study found that on average a grind in Ireland costs €35. So this is our population mean, where the standard deviation of the distribution is €10. If 40 grind lessons are selected at random, find the probability that the sample mean is greater than €32. So in this case, we're going to use our z-score formula for the sampling distribution. And we're going to find the probability of x being greater than €32. And this is equal to the probability that our z-score is greater than, filling into our formula, x bar is 32 minus 35 all over standard deviation of 10 divided by sample size, which in this case is 40. When we tidy that up, we will get the probability that z is greater than minus 1.897. However, our normal distribution table on page 36 and 37 of our log tables does not have negative z values. So what we do is we say this is equal to 1 minus the probability z is greater than 1.897. Another issue is the normal distribution tables give probability values for z being less than or equal to a specific score. In this case, we have z being greater than 1.897. So, to sort out this problem, we insert 1 minus the probability that z is less than 1.897. When we tidy this up, we get 1 minus 1 plus the probability of z being less than 1.897. Two ones will cancel out, and we're left with the probability that z is less than 1.897. On page 37 of the log tables, you'll find a normal distribution table that contains the z value for 1.9. There is no z value given for 1.897, so we round to 1.9, which is the closest z value in our normal distribution table. And that gives us a probability value of 0.9713. So the probability x is greater than €32 is 0.9713. That concludes our discussion on the empirical rule and sampling distributions.